Okay.
Okay.
So now,
Now,
all right. So let's talk about a very important topic in chemistry. This topic actually applies to a lot of situations, including some situations in biology. And also, if you have to do organic chemistry, you're going to meet this a whole lot. And that's the whole concept of oxidation reduction, oftentimes abbreviated as a redox reaction. All right. So let's define these terms. So basically, in a redox reaction, what happens is that you have electron transfer from one substance to another. All right. Now, the substance that is undergoing a loss of electrons, we say that substance is being oxidized. While the other substance that is undergoing electron gain, we say that substance is reduced. And there is a memory aid that you might find useful for helping you to remember what is involved in redox reactions, and that is oil ring. Oxidation involves loss of electrons, reduction involves gain of electrons. All right, so I don't know if you find that useful, but you'll see this in some textbooks as a memory aid for helping you to remember what happens in a redox reaction. So, in every redox reaction, that's what happens. Something loses electrons and something gains, right? And you cannot have one without the other, right? You cannot have oxidation without reduction, all right? So another term that we need to be aware of is what is called the oxidation state. In some textbooks, they call this the oxidation number, right? And it's basically an indicator of the degree of oxidation of an atom in a compound, right? So basically the oxidation states, as I said before, also called oxidation numbers, right? So what we're going to look at first, before we look directly at redox reactions, we're going to look at the rules for determining the oxidation number or the oxidation state of an element in a substance, right? So let me see here. So the oxidation number is the charge the atom would have in a molecule or an ionic compound if the electrons were completely transferred, right? So here are the rules. The first rule is that any element by itself, any free element by itself, has an oxidation number assumed to be 0, right? So if you have sodium or chlorine or magnesium or titanium by itself, not combined with anything else, then its oxidation number would be 0, right? So these are all examples of free elements, and their oxidation numbers are 0 in each case, right? And it doesn't matter, by the way, as you can see, it doesn't matter if it's a diatomic molecule or a polyatomic molecule. If it's the same element within that molecule, then the oxidation number would be 0, all right? In monatomic ions, the oxidation number is equal to the charge on the ion, all right? So if it's a monatomic ion and there's a charge, that charge will be the same as the oxidation number. And here we have some examples. We have lithium ion, where the oxidation number therefore will be +1. The iron 3 ion, where the oxidation number is +3, and the oxide ion, where the oxidation number is -2. All right. So any monatomic ion, whatever the charge is on that ion, the oxidation number will be the same. All right. The third rule is a bit unusual. It says that the oxidation number of oxygen is usually -2, but there are some exceptions. And the exceptions would be hydrogen peroxide and any compound that contain the peroxide ion. In those cases, the oxidation number of oxygen will be -1. All right, the oxidation number of oxygen will be -1 in those cases. All right, but in other cases, if oxygen is combined with anything else, right, with sodium, whatever, then its oxidation number is -2. Okay, and then number 4 says the oxidation number of hydrogen is +1 in most cases, excepting when the hydrogen is bonded to a metal. If hydrogen is bonded to a metal, then the oxidation number of hydrogen in those instances will be -1. All right, so that's another special rule for hydrogen. The next rule says group 1A metals And I should probably add here in their compounds, not by themselves. So let me just add here. In their compounds. All right, so group 1A metals, the oxidation number is +1. Group 2A metals, the oxidation number is +2. And fluorine is always -1, right? If fluorine is combined with anything, then its oxidation number is assumed to be -1. So those are some of the special rules for specific elements. The sum of the oxidation numbers of all atoms in a molecule or ion is equal to the charge on that molecule or ion. And this rule is helpful for determining the oxidation number of certain elements that you cannot determine based on the previous rules, right? And I think I have an example lined up here, right? It says, what's the oxidation number of all the numbers, of all the atoms, I should say, in the bicarbonate ion, HCO3? Well, based on the previous rules, we know that hydrogen has an oxidation number of +1, right? And we also know that oxygen has an oxidation number of -2, right? But we don't know directly what the oxidation number of carbon is. However, based on the last rule, we know that the sum of the oxidation numbers of all the atoms in that ion must be equal to -1, because that's what the last rule says. The last rule says that when you add up all the oxidation numbers of all the atoms in a molecular ion, that sum will be equal to the charge. In this case, the charge is -1. So carbon is basically an unknown in this situation, right? So as we said before, oxygen is -2 in terms of the oxidation number, hydrogen is +1 in terms of the oxidation number, and carbon, we don't know what it is, right? So this is the setup. 3 times -2. The reason why I multiply this by 3 is because we have 3 oxygens here, right? So 3 times -2, which would be for the oxygen, +1, which would be the oxidation number of hydrogen, plus the unknown, which is carbon. That sum will be equal to -1. So it's a simple equation to solve for. And when you solve for the unknown, we see that carbon has an oxidation number of +4. All right? And that's basically how you can determine the oxidation number of pretty much any element in a molecule or ion. All right, any questions about the rules? Any questions? So based on this, you should be able to do question 9. In fact, let me help you out with maybe 1 or 2 of these. So, and then you can do the rest. So I'm just going to choose an arbitrary one. Which one should I choose? You tell me. Well, all right, I'll choose. I will choose this one, all right? So in this case here, in the case of this compound, I'll be honest, I don't know what the name of this compound is. But you have 4 hydrogens of silicon and 4 oxygen, right? So we know that the oxidation number of hydrogen is +1, right? So we have 4 times +1. We add that to X, which is the unknown for the silicon, plus 4 times for oxygen is -2. And because the entire thing is neutral, we set that to be equal to 0, right? So that's 4 plus X minus 8 equals 0, which means that X minus 4 is equal to 0, which means that X is equal to +4. So the oxidation number of silicon is +4. All right? And that's basically how you're going to do the others. Do I need to do another one to show you how to do it? It should be easy. As long as you keep in mind the rules, right? Hydrogen is +1 in most cases, except when bonded to a metal. In fact, I think I have one. Which one is it? Right. In this case here, hydrogen is bonded to a metal. So in that case, the oxidation number is what? According to the rules. If hydrogen is bonded to a metal, the oxidation number of hydrogen in that case would be -1. Exactly. So you have to be careful. I think that's the only example. Yeah, I don't see any example of any other example of hydrogen bond. So you have to be careful, right? If hydrogen is bonded to a metal, then the oxidation number is -1. But if hydrogen is bonded to anything else, a non-metal or metalloid, then the oxidation number is +1. All right. So, so now we're going to talk about what happens in a redox reaction. In a redox reaction, as we said before, we have an electron transfer from one substance to another. So I think I mentioned before that oxidation is where you have the loss of electrons. What also happens in oxidation, for that particular element that is undergoing oxidation, there will be an increase in the oxidation number, right? So the loss of electrons corresponds to an increase in the oxidation number. And the converse is true. A gain of electrons results in a reduction in the oxidation number, all right? So we can define oxidation and reduction in terms of loss or gain of electrons, but we can also talk about oxidation reduction in terms of increase or decrease in the oxidation number, all right? So let's look at this example. This is a relatively simple example of a redox reaction. Now this reaction here is the reaction between copper sulfate and magnesium. And as you can see in this picture to the left, basically what they did was that they put a coil of magnesium in a solution of copper 2 sulfate. Copper 2 sulfate is blue due to the copper 2 plus ions, right? So you insert the magnesium into the solution of copper and then you wait a while, and then what will happen? You'll observe two things happening. One is that the solution will start clearing up. The blue color becomes less and less intense, right? So what that tells you is that the copper 2 plus ions are being removed from the solution. And then another thing that you'll observe is that you're going to see some deposits on what is remaining on the magnesium, right? So this is the actual reaction that is taking place. CuSO4 aqueous plus magnesium solid to give magnesium sulfate plus Cu solid. And this should be aqueous here, right? So as I said before, the blue solution will start clearing up, and that's because the copper 2 plus ions are being removed to form the copper solid from the solution, right? So the blue color will become less and less intense, as you can see going from here, to this picture right here, right? You see it becomes colorless pretty much, and you see some deposits left on the magnesium, and that deposit would be the copper solid being formed. The magnesium sulfate will remain in solution. Now, if we were to write down the net ionic equation, if you go through the same steps as we did in the previous assignment questions, because copper 2 sulfate is ionic and aqueous, it will split up to form Cu2 plus aqueous plus SO4 2 minus aqueous, right? Plus magnesium. And then on the right side, the magnesium sulfate, which is also in an aqueous solution, will split up to form Mg2 plus aqueous plus SO4 2 minus aqueous plus Cu. All right. So what's going to happen is, well, firstly, let me ask you this. What would be the spectator ion in this case? What would be the spectator? Remember, the spectator ion remains unchanged going from left to right. Exactly, the sulfate ions would be the spectator ions, right? So therefore, the net ionic equation, I'm going to write it down here, is Cu2 plus aqueous plus Mg solid to give Cu solid plus Mg2 plus aqueous. So this, folks, would be the net ionic equation, right? And if you look at this equation here, you'll see where redox is actually taking place, where one substance is being reduced and another substance being oxidized. Let us look at the changes that the copper 2 plus underwent, right? So basically, you start off with copper 2 plus here, and you end up with copper solid here, right? This has no charge, and the copper 2 plus has a plus 2 charge, right? So basically, you have a reduction in charge, right? So basically, the copper 2 plus is undergoing reduction, where it gains 2 electrons. So I'm going to put plus 2 electrons here, right? The copper 2 plus gains 2 electrons to form the copper solid. Where do those 2 electrons come from? It comes from the magnesium undergoing oxidation. The magnesium solid, which has no charge, will lose 2 electrons, right, to form the magnesium 2 plus, right? So therefore, the magnesium is undergoing oxidation, right? Because it is losing electrons, and therefore its charge or oxidation number will increase, and therefore the magnesium will undergo oxidation, while the copper 2+ will be undergoing reduction. And this is what happens in every redox reaction. And one thing I want to point out too, which will become important when we look at questions, well, not so much 10, but let me see here. Question 12. All right. So very important. In every redox reaction, the number of electrons lost in the oxidation process must be equal to the number of electrons gained in the reduction process. That happens in every single redox reaction. The total number of electrons lost will be equal to the total number of electrons gained, right? So that is one of the things that you have to ensure when it comes to balancing redox equation. Okay, so let me talk, well, before we, let me see here. Let me go back to the assignment quickly, and I want you to look at question number 10. Okay, we're there. Okay, I thought I had it here. Oh, here it is, okay. So question number 10 says, in each of the following reactions, determine what is oxidized and what is reduced. So let me hear what you have to say about this one. Determine what is oxidized and what is reduced. The key to answering this question is to look at the changes that each element undergoes as you go from reactant to product, right? So in the case of calcium, the oxidation number is what on the left side? What's the oxidation number of calcium on the left side? Well, what did we say about elements by themselves? What did we say about elements by themselves? Elements that are not combined with anything else. 0. So the oxidation number of calcium here is 0. Now, the question I have to ask you here is, what is the oxidation number of calcium in the case of calcium oxide? One, you sure about that? Calcium oxide. What's the charge on the oxide ion? -2, right? Which means that the charge on the calcium ion is what? +2, exactly. So the calcium on the right side is +2. The calcium on the left side is 0. So basically, there's an increase in the oxidation number for calcium, right? So therefore, the element being oxidized will be the calcium. All right. Now, the next question is, what is the element being reduced? Now, let's look at water, right? What is the oxidation number of hydrogen in water? Again, you need to go to the rules. What is the oxidation number of hydrogen in water?
2 + 1.
+1. Hydrogen is always +1, excepting if it's in hydrogen peroxide. What is the oxidation number of hydrogen on this side? On the right side? 0. So in the case of in the case of hydrogen, what is happening? You're reduced from +1 to 0, right? So therefore, it's a hydrogen that is undergoing reduction. All right? Any question about this one? Any questions? Okay, so if you understood what we did in 10A, what's the answer in 10B? Clear this here. And scroll down. Okay, so which element is being oxidized? We have to, again, we have to look at each element and the changes that you're undergoing, going from left to right, all right? So let's look at the hydrogen. What's the oxidation number of hydrogen here? On the left?
2.
0. And what's the oxidation number of hydrogen here? +1. So therefore, hydrogen is being oxidized because its oxidation number is increasing as you go from left to right. And then that means that the oxygen here, which was 0 here and -2 here, that is undergoing reduction. So therefore, it's oxygen that is undergoing reduction in this case. All right? Any questions about this one? Any question? Any questions? Okay, moving along. Let us, whoops. Should have done that. I should clear this first. Let us talk about balancing redox equations. Very important skill that you need to master. And let me just say that when it comes to balancing redox equations, go to the PowerPoint. You could do it the traditional way, the way that we're accustomed to, but for some of these equations, that would be very, very time consuming, all right? So there's a method that is used for determining, for balancing equations of this type, redox equations. In some textbooks, they call it the ion-electron method. So let me just go through the steps involved. And the best way to learn this, in my opinion, is to go directly into an example. Now, this question is asking for you to balance an equation which is described here as Fe2 plus going to Fe3 plus by Cr272 minus. Now, to be fair to you guys, this is not enough information. So what I'm going to do is add something here. What should I word it? Producing Cr3 plus, chromium 3 plus ions. All right. You need that additional information in order to answer this question. All right. So how do we go about balancing this particular redox equation? The very first step is that you write down an unbalanced equation based directly on the information that's provided. So basically, in this case here, we know that Fe2 plus go to Fe3 plus. So one of the reactants would be Fe2 plus, and one of the products would be Fe3 plus. And the statement says that Fe2 plus is oxidized by dichromate, Cr2O72 minus. So therefore, there are two reactants. One is Fe2 plus and Cr2O72 minus. And then on the product side, you're going to have Fe3 plus and Cr3 plus, right? So this equation is straight up unbalanced. So the next step is that we separate it into two half equations. One half equation would be the oxidation half equation, and the other half equation would be the reduction, right? So in the case of the oxidation half equation, you're going to have the Fe2 plus going to Fe3 plus, and in the case of the reduction half equation, you're going to have the dichromate going to the chromium 3 plus ion. All right? So that's the next step. You separate the unbalanced redox equation into two half equations. The next step is that you balance all atoms excepting oxygen and hydrogen in the traditional way that we're accustomed to. Now, in the case of the first half equation here, you have one iron on both sides, so therefore you don't need to make any changes there. However, in the case of the second half equation, you'll notice that you have two chromiums here, and you have only one here, right? So to balance chromiums, you have to put a 2 here. So this will be the result, right? 2 chromium ions here to balance with the 2 chromiums on the left side, all right? Okay, the next step is that we balance the oxygens. Now, how do we balance the oxygens? We balance the oxygens by adding water to one side which is deficient of oxygen. And this step here, I should have divided it into 2 steps, but anyway, I'm just going to describe it stepwise. So basically, we add water molecules to the side that is deficient of oxygen so that we end up with the number of oxygens on both sides being the same. Now, for the first half equation, we don't need to do anything as far as that's concerned. Can you see that? Okay, let me see if I can, all right, you know what? Let me just do it on this here. In the interest of time. Okay, so what we had was Fe3 plus, I'm sorry, Fe2 plus going to Fe3 plus. And what was it? Dichromate, Cr2O72 minus, going to 2Cr3 plus. All right. Now, I was saying that to balance the oxygens, we would add water molecules to the side, which is deficient of oxygens, and we add enough so that we have the same number of oxygen atoms on both sides. I was about to say that in the case of the first half equation, it's up here. In the case of the first half equation, there are no oxygens involved, right? So we don't need to balance any oxygens for the first half equation. However, for the second half equation, we have 7 oxygens here, right? So according to what we just described in terms of the steps, we need to add 7 water molecules on the right side to balance the oxygens, all right? Okay, so that's how we balance the oxygens. We balance the oxygens by adding water molecules. And you notice that I add the water molecules to this side so that there is enough oxygens here to balance out with the 7 oxygens on the left side. Now, the next step, according to the steps I have in the PowerPoint, is that we balance the hydrogens by adding H plus ions to the side, which is deficient of hydrogen ions. Again, you don't need to make any changes here in the case of Fe2 plus going to Fe3 plus, because there are no hydrogens involved. However, in the second half equation, you have a total of 7 times 2, 14 hydrogens on the right side, which means that we add 14 hydrogen ions on the left side to balance the hydrogens. All right? Okay, so remember, to balance the hydrogens, we simply add enough hydrogens to one side so that we end up with the number of hydrogens on both sides being the same. All right? Now, the next step is where students frequently screw up. All right, so I'm going to go through it slowly so that we're all on the same page, right? The next step is to balance the charges, right? Because we have to make sure that the charges are the same on both sides of each half equation, right? So the way we balance charges is that we add electrons to the side that has a net higher charge. And we add enough electrons so that the charges become the same. So in the case of the first half equation, you know that the total charge here on this side is plus 2. The total charge on this side is plus 3. So the question becomes, to which side do we add electrons and how many? And the answer is, we add 1 electron to this side. Because by adding 1 electron to this side, the total charge on this side will be 3 minus 1, which is plus 2, which balances with the plus 2 on this side. All right? Now, the second half equation is a bit more complicated, but it's the same principle, right? So we look at both sides to see how many charges total do we have. On the left side, we have a total of 14 plus charges minus 2. So that's a total of plus 12 charges, right? On the right side, we have 2 times plus 3, which is 6. Water is neutral, so the total charge here is plus 6, right? So in this particular case, as we said before, to balance the charges, we add electrons to the side with the net higher charge, which would mean that in this case, we add it to the left. So the question now becomes how many? Remember now, each charge, each electron has a minus 1 charge, right? So the question is how many negative charges or how many electrons do we add here to reduce a total of plus 12 to plus 6? Exactly, so we add 6 electrons here. So by adding 6 electrons here, you reduce this to plus 6 on this side, which balances with the plus 6 on the right side, all right? So let me emphasize again, because as I said before, students tend to, especially when they're learning this for the first time, to balance the charges, you add electrons to the side with the net higher charge. And you add it up so that you lower the net higher charge to be equal to the other side, and therefore the charges will be the same. All right. So now that we have balanced all the atoms and we have balanced the charges, the next step is something that I alluded to earlier. Remember I said that in every redox reaction, the number of electrons lost must be equal to the number of electrons gained, right? Now, as we have it right here, that's not the case, because the number of electrons lost here is 1, and the number of electrons gained here is 6, right? So how do we achieve the number of electrons lost and gained being the same? And the answer in this case is that we take this equation and we multiply it by 6. Because when we multiply this by 6, we're gonna end up with 6 electrons, right? Which is the same as the 6 electrons on this side. But we have to multiply everything by 6, right? So this becomes 6 Fe2 plus to form 6 Fe3 plus 6 electrons. All right? So that's how we achieve the electron balance, right? Then what we have to do is we have to add this equation to this equation, and in so doing, we have to cancel out all common items on both sides. Let me just erase this to avoid confusion. So basically, we'll be adding both equations together. We cancel out those items that are common to both sides. Now, in this case here, that will mean that these 6 electrons will cancel out these 6 electrons. And we simply write down what is left. So what is left? 6 Fe2 plus 14H plus to give Cr2O72 minus. And then on the right side, we're going to have 6 Fe3 plus 2 Cr3 plus 7 H2O. And that, folks, should be the final answer. However, I always tell my students when they're doing this is to check to make sure that everything in the final equation is balanced, right? So let's do that now. Let's start out with ions. We have 6 ions here. We have 6 ions here. So the ions are balanced, right? We have 14 hydrogens here, and we have 7 times 2, 14 hydrogens, so the hydrogens are balanced, right? We have 2 chromiums here. We have 2 chromiums here, so the chromiums are balanced. And then the oxygen, we have 7 oxygens here, and we have 7 oxygens here, the 7 water here, that makes that 7 oxygens. So the oxygens are balanced. We also have to look at the charges to make sure that the charges are balanced, right? So let's do that. We have a total of plus 12, plus 14, minus 2, right? So that gives you a total of what? 26 minus 2, that's 24, right? And then on this side, we have 6 times 3, 18. So that's plus 18. And 2 times plus 6. 2 times plus 3 gives you plus 6. And that also is equal to plus 24. So basically, the equation is now balanced, right? Everything is balanced, including the charges. All right? Okay, any questions about this? Any questions? Any questions? So, based on that, we can do question number. Oh, by the way, question number 11. I skipped over that. Basically, you're going to use the same rules for determining the oxidation numbers for all the elements in number 11, right? So you can do that. At the top, you're supposed to write down let me see here. Oh, you're supposed to write down the name, right? So for example, let me go to that. Okay, so like for example, in this case here, K3PO4, you're to write down the name of the compound, which is potassium phosphate. And then you're going to find the oxidation numbers of each of these elements, right? And that's what you're going to do for all of them, okay? All right, so you should be able to do that. But if you have any questions, of course, please let me know. Okay, let me scroll down to the first of the balancing of equations, right? Balancing of redox equation. So the first one, you're given the unbalanced equation. So what's the first step? Let me hear what you have to say about the first step. You can look in your notes that we just covered. What's the first step in balancing any redox equation? Right, 2 half equations. So Mn2 plus the form MnO4 minus and BiO3 minus to form Bi3 plus, all right? Okay, what's the next step? Based on what we did earlier, the example we did earlier. Before that. You're going to balance oxygen later, but there's a step before. After separating into two half equations, the next step is
Finding what's oxidation, what's reduction.
well, I mean, we already okay, but I mean, we know that this is oxidation.
Yeah.
And this is reduction. But there's an important step after separation of the two half equations. There is an important step. Balance all atoms excepting oxygen and hydrogen, right? Now, in this case, we don't need to do anything because they're all balanced, but you need to take that step into account because you may need to balance like we did in the previous example, right? Okay, so after that step, what will be the next step? What you said, we balance the oxygen. How do we go about balancing the oxygen? Let me just erase this here. You add water, right, to balance the oxygen. Okay, so for the first half equation, to which side would you add water and how many water molecules would you add? To the left side. How many water molecules would you add to the left side? 4 water molecules. Okay, very good. What about the second half equation? To which side would you add water and how many? To the right, how many? 3 water molecules. Very good. All right. So that's how you balance the oxygens. What's the next step? Balance the hydrogens. How would you go about balancing the hydrogens?
And H2 silent.
No, not H2. H what?
H plus.
H plus. Hydrogen ions, right? Okay, so for the first half equation, to which side would you add the H plus and how many? To the right side, how many? 8 hydrogen ions. Okay, very good. For the second half equation, to which side would you add hydrogens and how many?
The left side.
Left side, how many?
6.
Okay, very good. All right, so now we get to balance the charges. Let's see if you can do this without screwing it up, all right? So to balance the charges, for the first half equation, to which side would you add electrons and how many? Remember, to balance the charges, to which side do we add it to? We add it to the side with a higher net charge, right? Okay, so for the first half equation, which side will you add the electrons and how many?
Side 1.
Left side, you sure about that? What's the total charge on the left side? +2, right? What's the total charge on the right side?
Negative.
Hmm?
4.
7.
Exactly, +7. Because there are 8 plus charges -1. All right? Okay, so to which side will you add electrons and how many will you add? To the right, how many? 5 electrons, exactly. Because by, oops, okay, move slide. Because by adding 5 electrons, you're adding 5 negative charges, which reduce the +7 to +2 on the right side. Okay. Second half equation. To which side will you add electrons and how many will you add to that side?
The left one.
Left side, how many?
2.
Hmm?
2. Two making 3. 6.
This is +5.
Yeah,
This is +3. Yeah, 2 electrons. Exactly. Yeah, you're right. Okay, very good. So now that we have balanced the charges, what's the next step?
5.
What's the next step after balancing all the charges and everything else?
Make sure how much charge you gain, same with how much you lose.
The number, exactly, the number of electrons lost and gained should be the same. How would we achieve that? Because in one case, we have 5 electrons being lost, And then in the second half equation, we have two electrons being gained, right? So how would you equalize those electrons?
Multiply both, like the top and bottom.
You have to multiply both of them by certain numbers. What would you multiply the top one by?
Okay.
Two. Multiply the top one by 2. So when you do that, you're going to end up with 8 water molecules plus 2 Mn2 plus to give 2 MnO4 minus plus 16 hydrogen ions plus 10 electrons. Okay, what about the second half equation? Multiply this by 5. So multiply that by 5, you're going to end up with 10 electrons plus 30 hydrogen ions plus 5 BiO3 minus to give Bi3 plus, I'm sorry, 5 Bi3 plus 5 3 is 15 H2O. All right, okay. And then the next step is to
Yes, on these.
cancel out the electrons. But not only that, we need to cancel out the waters. In fact, these 8 water molecules here will cancel out 8 of these, leaving behind 7. And these 16 hydrogen ions will cancel out 16 of these, leaving behind 14. Right? So in this case, whoops, 7 here. In this case, not only do we cancel out the electrons, but some of the water and some of the H plus ions will cancel out, right? So we'll be left with 2 Mn2 plus 14 hydrogen ions plus 5 BiO3 minus to give you 2 MnO4 minus plus 5 Bi3 plus 7 H2O. All right. And then, as I always say, check to make sure everything is balanced in the end, right? Let's do that now. We have 2 manganese on this side, 2 manganese on that side, so the manganese are balanced. We have 14 hydrogens on the left side, and we have 7 times 2, 14 hydrogens on the right side, so the hydrogens are okay. We have 5 bismuth on both sides, here and here. And then as far as the oxygens are concerned, we have 15 oxygens on the left side, and we have 2 times 4, 8, 8 plus 7, 15 oxygens, right? And then finally, the charges. We have to make sure that the charges are balanced as well. So on the left side, we have plus 4, plus 14, minus 5. So that gives you what? That's 18 minus 5. That's 13, right? And then on the right side, we have minus 2 plus 5 times 3, 15. So that's 13 as well. So everything is balanced. All right? Any questions about this one? Any questions? Okay, let me clear this here. And I want you to try right now because I want to make sure that you guys master this particular skill, very important skill. I want you to try this first. I want you to try it now, and then tell me what you did. Let's follow the step
as
I'm right back.
Down my balance, on a balance sheet, then I found a charge for appeal to that five.
Okay.
So
But, well, firstly, let me see here. Okay, so basically, when you look at the charges on the left side here, that's -4. And that's -2. So there's a difference in charges, so you have to ask yourself, which side will you add electrons? And how many to make sure that the charge. You add electrons to this side,
Okay,
because that side is a higher net charge. Okay, we
Okay, are we
finished?
finished?
No.
Great news. My 1-year-old is walking.
Alright, so let's hear what you have to say about this question. So let's see if you can do this with minimum help from yours truly. So what's the first step?
First step is write down two half equations.
Okay, so one half equation would be MnO4 minus to Mn2 plus. And the other one is S2O3 2 minus to S4O6 2 minus. Okay, what's the next step?
The balance the equations.
Balance what?
Balance the oxygen.
I'm sorry?
The oxygen.
No, we balance what?
So
We balance the all atoms accepting.
oxygen.
Exactly. So what does that mean for this equation here? We have to multiply this by 2 to get the sulfur balancing, right? The manganese is already balanced, so we don't need to do anything to that. Okay, next step.
Balance the oxygen.
By,
Adding of H2O.
okay, so for the first half equation, to which side will you add H2O and how many?
To the right side, add
4 water molecules on the right side. And what about the second half equation?
You don't need to because the.
Right, because you have 6 oxygens here, 2 times 3 is 6, which balances with the 6, so therefore you don't need any water in that case. The next step is what?
Hydrogen.
Balance the hydrogens by,
Add 8 hydrogens to the left side.
and please remember it's 8 hydrogen ions, right? Okay, and in the case of the second half equation, we don't need to add any hydrogen because there's no hydrogens involved, right? Next step.
Balance control. Oh no, I mean.
You're right, balance the charges.
Yes.
So that means for the first half equation, to which side will you add electrons and how many?
Add to the left side.
How many to the left side? 5 electrons. All right, and then what about the second half equation? To which side would you add electrons and how many?
Add to the right.
To the right side, add 2, because you have a total of -4 here, -2 here, which means that you need 2 electrons to get the charges balanced. Okay, next step.
Next step, we have to, make sure that how many items you give, how many takes the same.
Here and here, right? So what do we multiply this by?
Top by 2.
Okay, so if we multiply the top equation by 2, we're gonna end up with 10 electrons plus 16 hydrogen ions plus 2 permanganate ions. And then on the right side, you're gonna have 2 Mn2 plus 8 hydrogen, 8 water, right? And what about this equation here? What do we multiply that by? 5. So you're gonna end up with 10 S2O3, 2 minus, to give 5 5 S4O6, 2 minus, plus 10 electrons, all right? So the next step is to add these two, the electrons will cancel out, and there's nothing else to cancel out, so we just write down what's left, which would be 10 S2O3, 2 minus, plus 16 hydrogen ions, plus 2 MnO4 minus, and then on the right side, you're gonna have 2 Mn2 plus 8 H2O, plus 5 S4 O6 2 minus, and then we check to make sure that everything is balanced, right? Starting with the sulfur, we have 2 sulfur, 2 times 10 sulfur here, that's 20, and that balances with the 20 on the side. We have 30 plus 4, 8, so we have 38 oxygens on this side. Here we have 8 plus 5 times 6, 30, 30 plus 8, 38, so the oxygens are balanced. And then for the hydrogens, we have 16 hydrogens here, 8 times 2, 16 hydrogens, so that's balanced. We have 2 manganese here, 2 manganese, and then as far as the charges go, we have minus 20 plus 16 minus 2, so that gives you what?
-6, or
16 minus 2 gives you 14, yeah, minus 6. And then on this side here, we have plus 4. And here we have 5 times minus 2, so that's minus 10. So that's minus 6 again, so the charges are balanced as well. Yes, sir.
For the equation, like the final equation, doesn't matter which way you write it, or
I'm sorry?
doesn't matter for final equation, doesn't matter which way you write it.
Which way? Like,
I put 2M04 first, and when you have yours.
oh, yeah, that doesn't matter. As long as you have the reactants on the right side, I'm sorry. As long as you have the reactants on the left side and the products on the right side, it doesn't matter the order on each side. Same thing. All right, any other questions about this? Any other questions? All right, so based on what we have done, you should be able to do, let me just do a quick check here. Let me clear this first. You should be able to do that one, and that's it for this assignment. So what I'm going to do now is set up a Dropbox. So let me go here. Let me go here. Let me go grade. No, not grades, assignments. Assignments. And this is assignment 4. Okay, so today is the 26th of May, 2026. Oops. Okay, so I'm going to let this be due on Thursday, May 28th. And save. So now it should be available. So make sure you upload it into that Dropbox. And make sure it's in PDF, please. Some of you, well, I don't remember if it's this class or the other class I'm teaching, but yeah, some of you have been leaving your assignment in I've seen a couple of JPEG formats, which I can't print from Canvas for some reason. I don't know what's going on. I don't know why they designed it that way, but that's what it is. All right. So now we're going to move on to chapter 5, which deals, oh shoot, it's 7:30. Okay, I need to get a start on chapter 5. So chapter 5 deals with gas laws. All right. And again, this is something, I'm going to go through this rather quickly because again, this is something that you guys should have encountered in your introductory high school. There are a couple of additional topics which you may not have covered, but for the most part, this is going to be a rehash of what you learned in your previous chemistry experience. The questions may be a bit more challenging. That's the only difference I would say. But the topics and all the other related stuff should be the same. All right. So let's talk about gases. We all know what gases are like. Basically, if you look at gases at the microscopic level, we know that gases are comprised of small particles, high energy particles, always moving around, occasionally hitting each other and bumping into the walls of the container that they're in. All right. So that's basically the perspective at the microscopic level. That translates into certain properties that gases display. For example, we know that gases easily float, right? If I have a bottle of ammonia right here and I open it up, eventually you guys at the back would smell it. I would, of course, smell it first, but you guys at the back would smell it because basically gases tend to spread. Now, there's a term that is oftentimes used, vapor, right? Vapor is referred to a substance which is a gas, but it's a liquid on a normal room temperature condition. So therefore, we refer to water vapor or methanol vapor, but other gases like oxygen and so on, which exist under normal room temperature conditions as gases, we simply call them gases, all right? And what you find is that many low molar mass liquids will easily vaporize to form gases. And this is particularly true for organic solvents, all right? Okay, and this is just a list of gases and, industrial use. Just to highlight a couple of examples. Chlorine is used as a disinfectant and bleach. Ethylene is used in the manufacture of plastics. Methane is used as a fuel and also used in the industrial manufacture of hydrogen. So these are just different gases and their typical use, all right? Now we can explain the behavior of gases by what is called the kinetic molecular theory, which I kind of alluded to when I described the behavior of the gas particles. So this is a theory that is used to explain all the gas laws that we're going to meet later on. And basically, as I said before, what this theory says is that the gas particles are moving at high speeds, right? Random speeds. They tend to move in straight lines until they hit the walls of the container or hit each other. And we call that motion, that straight line motion, we call it translational motion, all right? Now, based on that understanding, we can understand, for example, why gases exert pressure on the inner walls of the container, right? And that is due to the continuous bombardment of the gas particles against the wall of the container. And collectively, that manifests itself as a pressure being exerted against the wall of the container, all right? And then we can understand the relationship between the temperature and certain properties that gases exhibit. So for example, we can understand the relationship between temperature and pressure. If you increase the temperature of a gas, the pressure it exerts increases. And the reason why that happens, using the kinetic molecular theory, the reason why that happens is because when you increase the temperature, you're imparting more energy to the gas particles. The gas particles will move around more quickly, greater speeds, will hit the walls of the container more rapidly and with greater speeds, and therefore, as a result, that would result in an increase in pressure of the gas exerted on the walls of the container. So let's talk about gas pressure. We have to define that first because people tend to use pressure and force as they mean the same thing, but they're not the same thing, right? Let me tell you what a force is. Force is basically a push or a pull, right? So if I push on, let's say, this button right here, I'm exerting force on the bottom, all right? Pressure is a bit different. Pressure is a force transmitted over a particular area, all right? So pressure is not just force, pressure is what happens or what you observe when force is transmitted over a particular area. And therefore, the relationship between pressure and, I thought I had the equation. Okay, so the relationship between pressure and force is this. Pressure is equal to force divided by area, all right? Now, as a result of this equation here, the units of pressure can be expressed as some unit of force divided by some unit of area, right? So the SI unit of force is newtons, the SI unit of area is meters squared, which means that the area, I'm sorry, not the area, but the units of pressure would be newtons per meter squared, all right? So that's one unit of pressure, but there are other units as well, right? You have what is known as the Pascal unit, and then you have the larger unit in relation to the Pascal unit, which is called the kilopascals. You have the atmosphere and you have the millimeters mercury unit, which is the same thing as the torr unit, right? So the next slide shows you the relationship between those units, right? So we have 1 atmosphere on this side here, and I'm going to explain how that 1 atmosphere unit came about. But 1 atmosphere will be equal to all these units that you see here, right? And I would say that for the most part, for our purposes, we will be using, we'll make a check mark here. We will be encountering this unit, this unit, this unit, this unit, and this unit, right? The other units, I doubt very seriously that we're going to encounter or use those in any problem-solving situation, right? So these are the different units, and these are the different relationships between those units. These units are also in the tables, so you don't have to memorize the relationship, but you need to know how to use them, how to convert from one to the other. In fact, I think the next slide is a question. Oh no, I thought next slide was a question. Okay. Okay, I'm going to talk about barometers and then stop for today, all right? So how do we measure the pressure of the atmosphere? Because you know the atmosphere is a collection of gases. The major component is nitrogen, then oxygen, and then you have some trace gases, right? So this is where you're going to see the atmosphere unit come into play, right? Basically, we take a trough filled with mercury. In fact, we have two setups here, right? You have this trough and this trough filled with mercury, and then you insert a tube in each of them. Now, the difference between these tubes is that this one has an open end, right? Both ends are open, but in this case, the open end is submerged in this mercury trough here, and the closed end is up here, all right? So in this case here, what you'll find is that the mercury level inside the tube will be the same as the mercury level outside. They'll be the same level. And the reason why is because the atmospheric pressure that acts on the surface here, on the outside of the tube, will be the same atmospheric pressure which acts inside the tube on the mercury surface here. So they're equalized, and therefore, as a result, the mercury levels will be the same inside and outside of the tube. On the other hand, in the case of this setup, the way you set it up is that you would fill the tube with mercury, and then you'll put your thumb on the open end. Of course, you should be wearing gloves for this, right? You put your thumb on the open end, and then you insert it into the trough, right? And then you remove your thumb. Now, if the tube is long enough, what will happen is that the mercury level will fall until the height of the mercury column is about 760 millimeters, right? So what this indicates is that the mercury column here will exert a pressure at this level here, which will be the same as the atmospheric pressure. So therefore, we can use the height of the mercury column as a measure of the atmospheric pressure, because if the atmospheric pressure, if the atmospheric pressure here increases, what that happens is that it pushes up the mercury inside the tube, right? So therefore, we can use the height of the mercury level inside the tube as a measure of the pressure exerted on the surface outside the tube. So therefore, that's basically the mercury barometer, which is used to measure the atmospheric pressure, all right? So basically, this is where the millimeter mercury unit comes in, right? According to the setup and so on, what was decided by the powers that be, that 1 atmosphere, right, pressure will be equal to 760 millimeters mercury. So that's why, let me go back to the previous slide. That's why we have this relationship here. 1 atmosphere is equal to 760 millimeter mercury, and the Tor unit, named after a very famous Italian scientist, Torricelli, they decided to basically say that, okay, the millimeter mercury unit would be the same thing as the Tor unit, all right? One more thing I want to say, and then I'm going to stop. I neglected to mention, go back here, that there's a special name given to the Newton per meter squared unit. This is also called the Pascal unit, right? So the Pascal unit is the same thing as the Newtons per meter squared. And you can, but usually, for a lot of these calculations, the kilopascal unit is used, right? So basically, that's what you see, and that's why you see here, we have 1 atmosphere is equal to 101.325 kilopascals, which would be the same thing as 101,325 pascals, all right? Okay, I think I'm going to stop here for today. The next class, we're going to talk about another instrument known as a manometer, which is used to measure the pressure of a gas, but that's for our next class, all right? Let me remind you that your test is coming up on Thursday. I've decided to go easy on you guys and test you only on chapters 1 and 2, all right? I have posted, okay, what have I published? I've published the answer key to assignment 1. I've not yet published the answer key to assignment number 2. I'm going to do that this afternoon, so that you can have it to review. And also, what I'm going to do is, I'm going to publish a past test. So let me see if I can locate it, which should help you. Okay, let me see what this has. Oh, okay, so let me see, test number 1. Okay, let me see what this has. Okay, this should be a good, okay, this should be a good review. Now, hold on. Did we do, I think we did this in chapter 3, right? Okay, so you wouldn't use that to prepare for chapter 3. But yeah, some other topics here. Yeah, so okay, so what I'm going to do is I'm just going to publish the whole folder, and then you guys can so this is past test answer keys. Yeah, I'm just going to publish the whole folder, right? Because it contains the answer keys for test 1, 2, and 3 and final exam and so on. So you can use that to help you to prepare as well. All right. If you have any questions, of course, please feel free to contact me. I'll be in my office. Tomorrow is Wednesday, right? So I'll be in my office tomorrow from 1 to 5. All right. If you have any questions. All right. Okay, so that's it, folks. I'll see you guys in the lab in the next hour or so.
Is the test, you see the test folder, like the same one for my same test?
Sorry.
For the test, for the test one that's in the test folder, that's the same thing, like something that will look like?
Yeah, but as I said before, like there's one topic I just saw that was not covered by tests. Not covered by chapters 1 and 2. So we can ignore that for now. Because I'm sure that will come up in test number 2. Okay.
You know,
Yes, sir.
no, there's Simon. Over rest of that. You know.
Mhm.